All right, y'all. So we are moving on to chapter 9. 9.1 is all about our significance tests. So we're actually keeping the same theme of what we can do with samples versus populations, but we got a little more into claims about them. And then this kind of sets us up for the next couple chapters as well. We keep the same thing going. So two learning targets, we're going to look at correct hypotheses for what a significance test is about population proportions or means. So again, we're going to use the same type of values we've been looking at, and we're going to talk about what a p-value is. So this first thing says the reasoning of a test. So we have a claim here. It says Mr. Barlow claims to be an 80% free throw shooter. He goes down to the gym and shoots 50 free throws and makes 32 of them. Below is a dot plot that is a simulation of percent made for an 80% free throw shooter. So remember, we've seen distributions like this before. This is a sampling distribution of 400. So it tells us here 400 sets of 50 shots, right? So Mr. Barlow went down and did this one time. Well, we can use an online simulator to put in the data and see what it would be like 400 times. So he's claiming he's an 80% free throw shooter from this one sample. But if we did it over and over and over again, and he did the same 32, he got that 32 out of 50, we only have a couple times that that's actually happening. So based off these 400, right, and based off his one sample here, he's not really falling at this 80% mark. He's falling at way less than that. So this says, what does this make you think about Mr. Barlow's shooting percentage? So because of all this sample data now that we can compare his one sample to, we probably don't think that he's actually an 80% free throw shooter. Looks like he'd be less than that compared to our 400 sets. So we've seen like that stuff like this before. We've seen these distributions. We've seen questions like this using the graphs. So now we're just going to get into it a little more in depth, looking at these claims that we are testing. So in this case, we were testing if he was an 80% free throw shooter or if he was not. So those were our two claims. So moving more into this significance test, it says, so we make an assumption, and if our sample is unlikely when that assumption is true, then our assumption is a bad one. So that's what we just did, this part, using the sampling distribution to back up the claim. So what is a significance test that I keep talking about? So it's a procedure for using observed data to decide between two competing claims. So like I said, the above example was looking at if he was an 80% free throw shooter or if he was not. So those are my two competing claims. And we call these hypotheses. These hypotheses are always about the parameter. So remember, that's our population value. So we're always talking about, we want to find something out about our population. So let's look at the two different hypotheses that we have. So where we start a significance test by stating two hypotheses, one's called the null and one is called the alternative. So the null, this guy, is what we claim we weigh evidence against. Our alternative is the claim about the population that we are trying to find evidence for. So every time that we look at these, we want to try to find evidence for the alternative. The null is usually given to us in the context of the problem. So like above, the null would have been that he is an 80% free throw shooter. And then we're trying to find evidence against that. So just saying, okay, the alternative hypothesis is that he was not. So we're trying to find evidence for that using our graph. So let's use this next example to make those hypotheses from our context. So it says, does the job satisfaction of assembly line workers differ when the work is machine-paced rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half of the workers were assigned at random to each of the two groups. Both groups did similar assembly work, but one group was allowed to pace themselves while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 more weeks. So, actually, from back in the day when we talked about sampling and experiments, this would be one of those matched pairs because a matched pair experiment because we had random assignment. And then they also switched, so all the people did both sides of it. So we had two different groups, and they were getting exposed to both groups for the experiment. Anyways, so A says, describe the parameter of interest in the setting. So remember, the parameter is for the population. So what we're trying to find out here is the satisfaction of all workers. And the way they were testing that was having the one group work at the machine pace rather than self-paced. So that's how they were finding out the satisfaction of all workers. So now we want to make those claims. So it says state appropriate hypotheses for performing a significance test. So we're going to start with the null. So remember, the null is what we want to find evidence against. The alternative is what we want to find evidence for. So here, we're just going to say that the null is the satisfaction is the same when working at a fixed pace. So our null is just saying that, okay, no matter what way they have the workers work, their satisfaction is the same regardless. The alternative, what we want to find evidence for, is that satisfaction improves when working at their own pace. So again, we're looking for evidence to say that there's a difference, right? We're looking for evidence for this alternative. And all we're going to do in this first section is set up our hypotheses like this, be able to explain the hypotheses and make decisions about them. Next section, we'll do more of like solving with them, with proportions and means again. So it says the alternative hypothesis is one-sided if it states that the parameter is larger than the null hypothesis, or if it states that the parameter is smaller than the null value. So one-sided just means like I'm looking at the alternative value being greater than or less than the null. So in this case, like this example up here, we wanted to say that satisfaction improved. So that would be larger than our null. So our example above was one-sided. If it's a two-sided one, it states that the parameter is just different than the null hypothesis. So it could be either smaller or larger. So then we would just say, like, say the null value, like on our above example was talking just about satisfaction generally, then for our alternative, we would just say that satisfaction was just completely different, not being better or worse necessarily. So that's kind of like our first example with Mr. Barlow. We were just saying for like our alternative is that, okay, just that he was not an 80% free throw shooter, but we didn't say, is he better than 80% or less than 80%? So with symbols, we could just say different, not equal to. All right, so how do we make these decisions? We use p-values to help us decide what we actually have evidence for. Do we have evidence for the null, or do we have evidence for our alternative? So our p-value is probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence when the null is true. So it's a mouthful, but you'll get used to it as we keep working. So like I said, we use the p-value, so it's just a probability value, to make a decision about the test. My question is, do we want a small or large p-value? So this is important. We want a small p-value because what's that saying is that the small p-values are evidence for their alternative hypothesis because they say the observed result is unlikely to occur when the null is true. So we don't want the null to be true here. So we want evidence against it, and a small p-value helps us get that. And we'll explore this more in classes as well. So it says p-value being small, we can reject the null, which is what we want to do, and we can conclude that our alternative is true. The opposite is if the p-value is too large, then we fail to reject our null hypothesis, and we cannot conclude that our alternative is true. So we make that decision. We have this alpha level, so we have a significance level, and that'll be given to you, called alpha, and then that's what we compare our p-value to. Again, we're not doing that yet, just a little intro. The next part just says if the p-value is smaller than alpha, so some alpha levels we'll see are 0.01, 0.05, 0.1, they actually correlate directly with our confidence intervals. But it says if the p-value is smaller than alpha, we say that the data is statistically significant at that given level. In that case, we can reject the null hypothesis and conclude that we do have enough evidence to favor our alternative, which is our goal. So let's put this together in one last example. And again, we'll work a lot with this in class. This same thing with this section is that it's just an intro about this stuff, but we'll get way more in depth in 9.2 and 9.3. So if you're like a little sketched out right now, don't worry, we'll get enough practice. All right, so it says a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. A significance test is performed using the hypotheses. So our null is equal to 30 hours. Our alternative is greater than 30. So remember, we want to find evidence for our alternative, and that's saying that they would last longer than the 30 hours. Okay, so where mu is the true mean lifetime of the new deluxe AAA batteries, they give us our p-value. So they ran a test, and the p-value, the probability that we get is 0.0276. So when we interpret a p-value, what this is telling us is in the long run, so hopefully you remember that phrase from when we were just talking about probability in the first semester, there is a 0.0276 chance that we would get an X bar, or that means sample mean, remember, as large as we did or larger. So this one's a little weird because this example is a little weird because they didn't really give us, what X bar actually was from our sample. So that doesn't usually happen. But let's say X bar was, so from our sample, let's just pretend that the sample mean was 33. All right, so this already gives me evidence for my alternative, right? So the one sample gives me evidence already, which is a good start. So then we're saying that we have this 0.0276 chance that we would get this X bar as 33. So when we conclude, we look at this p-value compared to our alpha levels. So when we look at question B, it says, what would you conclude at alpha level of 0.05? So since 0.0276 is less than 0.05, we can reject the null and conclude the alternative, which is that the mean battery life really is greater than 30 hours. So that's good. This is what we wanted, right? We want evidence for the alternative. We have that here. So we can reject the null and conclude the mean battery life is greater than 30 hours. But if we change, so if we look at C, we're changing that alpha level. And there'd be different reasons to go about this. We'll talk about them later in this chapter. Now we're not smaller than the alpha level. So in this case, we'd have to say since 0.0276 is greater than 0.01, we fail to reject the null hypothesis and cannot conclude the alternative, which is the batteries lasting longer than 30 hours. So we just don't have enough evidence right now that it is greater. So main takeaways from this section is just that we're still trying to find something out about a population, but we're going to do that by testing claims from however we do our sample. So again, we use our p-values to help make decisions, whether we have enough evidence or we don't. But in the end, our goal is to hopefully find evidence for the alternative. In this case, they wanted their batteries to last longer than 30 hours because then they would make them and be able to sell their product. But if they weren't lasting longer than 30 hours, then it's dumb to put all that money into a new product when it's not different than their original. So just a little introduction on significance tests. We'll talk a lot more about it in class. We'll look at a lot of examples to get us familiar with what's actually going on here.